Hello students, I welcome you again on PhysicsWallah, and today we will be learning about alternating current. This alternating current chapter is very important in terms of practicality. I think you all know that electricity is generated at some place and being consumed at some different place. And sometimes the distance between generating station and the consumption point is more than 500 kilometers. So we need to transmit electric power from one point to other. And do you know that transmission of direct current, or you can say the DC current, is extremely expensive as compared to the cheap transmission of alternating current, and that makes this chapter very important. Okay, so before starting alternating current, we will learn about magnetic properties of matter. Okay, and then we will start discussing alternating currents, all factors, all parameters of alternating current, all practical you can say benefits of alternating current, and then we will learn what is the concept of resonance in alternating current circuits. Okay, so let's begin. So we will start learning magnetic properties of matter first. I think you all remember that if we place in magnetic field a magnet, say the magnet has some dipole moment or magnetic dipole moment. If there is some angle between magnetic dipole moment and magnetic field, the external magnetic field, a magnetic torque acts on magnet, and the torque is such that it tries to align magnetic moment vector along magnetic field. And if we let the magnet move freely, after some time, after few oscillations, the magnet will be aligned in the direction of magnetic field. The value of torque is mb sine theta. So here the torque acts, and when magnet is aligned along magnetic field, there is no torque as the angle between m and b vector becomes 0. So sine theta becomes 0. Okay. Actually, I also told you that if you have a charge circulating in a circular motion like this, it is also similar to a current carrying loop, and current carrying loop too has its magnetic moment. So this also behaves as a magnet, and if this current carrying loop too is placed in some magnetic field, this loop too experiences a torque, and finally if we let this loop move freely, it will be aligned along magnetic field. So if we look the atom carefully, we notice that there are many electrons in atom that are revolving around nucleus. So every electron must have its dipole moment, a magnetic dipole moment. Usually electrons are in pairs. In every orbit, in every shell, electrons are in pairs. But sometimes if electrons are in pairs, their spin is opposite. So the current because of one is cancelled by current because of two, because they have opposite spin. But in some cases, in some molecules, there exists an unpaired electron, a single electron in outermost shell. And if an atom has an unpaired electron, because of spin of this electron, the electron's orbit possesses some magnetic moment. And because of that, that atom possesses some magnetic moment. Okay. So we can say every atom of such material is a tiny magnet. Okay. But the material as a whole doesn't have any magnetic moment, because the magnetic moment of every atom is randomly oriented. Few atoms magnetic moment is facing towards right, so almost equal atoms magnetic moment is facing towards left, upward and downward. So because of this randomization, the net magnetic moment is 0 if we take a fresh magnetic material. Okay. But what happens if some magnetic field is applied? If some external magnetic field is applied, what happens? Every atom or every tiny magnetic atom experiences a torque, and that torque tries to align every atom's magnetic moment along the direction of external magnetic field. And if the atoms are free to move, okay, so what they do, they try to align themselves in the direction of magnetic field. However, in every material, this alignment is not highly perfect. Some atoms still are in random directions, but many atoms align themselves along magnetic field, and that is why this time if we add the magnetic moment of each atom and sum it up, we get some magnetic moment. Okay, so here we get some magnetic moment. Let us represent magnetic moment by a symbol mu. So here in external magnetic field, the sum of magnetic moment is not zero. And now we say this material has got magnetic properties. This material is behaving like a magnet. This material has some magnetic moment. Okay, so this happens when we apply magnetic field in a material whose atoms have unpaired electron in the outer shell. Okay, so now we know because of alignment here, the net magnetic field inside is actually different from what we have applied externally, because here in the material we have external magnetic field also, and we also have magnetic field because of these aligned molecules. Okay, so let us learn a little more in detail about magnetic materials. Okay, the first is magnetic intensity. The concept of magnetic intensity, I find it difficult for many students because in every books they don't explain it the way they should, I think. So let me try once to explain it. Suppose we have a solenoid. And if you pass a current in solenoid, I think you remember a magnetic field is generated inside the volume of solenoid, and that magnetic field is given by mu naught Ni. Let us understand each and every term precisely. What is mu naught? Mu naught is actually the property of medium inside solenoid. If we have vacuum in solenoid, if we have air in solenoid, this becomes the permeability of medium. So you can say it is the property of medium. Okay, and Ni, N is the number of turns in solenoid per unit length, and I is the current in that. So these two properties are related to coil. So they are properties of coil. So now we understand the resultant magnetic field inside solenoid has two components. Because it depends upon the properties of medium also, and it also depends upon properties of coil. So another way of saying is actually this coil creates some other influence. It creates a different kind of magnetic field that only depends upon the coil's properties, and that magnetic field, when interacts with the medium inside solenoid, after interaction we get resultant magnetic field B. Listen carefully. What coil does, when we pass current in coil, the coil creates a magnetic field, a special magnetic field that depends only upon the coil's properties. It is equal to Ni. And when this magnetic field interacts with the medium inside, then the net magnetic field is produced, and which is called B field or magnetic field, which is equal to mu naught Ni. So you can say this is something which is created by only coil. Okay, so that this is called actually the magnetic intensity or H vector or H field popularly. So H is defined as, for the coil, H is defined as B vector divided by mu naught. B vector divided by mu naught. So for a solenoid, I can say B is mu naught Ni, so H equals N times I. The magnitude H equals, I must say, the magnitude H equals N times I. So this H vector is the property of the current or current system generating magnetic field, and when H is multiplied by mu naught or permeability of the space in it, we get the net magnetic field. If we place some other medium, if coil is filled by some medium other than vacuum or air. Actually, vacuum, we can say there is no medium if there is vacuum, or if there is air, also there is no medium as density of air is very low. Okay, so the vacuums and air's permeability is same, that is equal to mu naught. But if the coil is filled by some medium, okay, then now the H vector becomes B vector divided by mu naught mu r, and mu r is called the relative permeability of that medium. The relative permeability of vacuum or air is simply 1. Okay, but it is not equal to 1 for any other medium other than vacuum or air. Okay, so this is called the magnetic field. Remember, this is produced by the current system. Okay, and when it interacts with the medium inside, it creates the net magnetic field. So you can say the H depends upon the system in which current is flowing. Okay. So actually we were learning intensity of magnetization. So let us go back. Yes, here. Now you know that if a magnetic field is placed around a magnetic material, and after all molecules get aligned in the direction of magnetic field and everything is got settled, okay, the magnetic materials may have some non-zero magnetic moment. They may have some non-zero magnetic moment. What is magnetic moment? The magnetic moment is actually the vector sum of vector moment of each molecules. Okay, so suppose we have added all magnetic moments of all molecules, and the total magnetic moment is mu vector. Mu vector is the total magnetic moment, remember. It is the total magnetic moment. So actually, the total magnetic moment divided by volume of the medium. Volume of the medium. This vector is called intensity of magnetization. Intensity of magnetization. This is something that is produced, that is induced, or that is generated inside magnetic material when we apply some magnetic field on it. Okay, so please remember the first term that we learn is H vector, then we have intensity of magnetization, and intensity of magnetization or M vector is simply the total magnetic moment of the material divided by volume. Okay. So as we know that if you have a solenoid, suppose, and we pass some current in it, the solenoid alone does not produces B field. It produces an H field. H field, or that is given by the H is given by the magnitude H is given by number of turns per unit length multiplied by current. The solenoid produces H field. Suppose we place a magnetic medium inside solenoid. What happens then? The molecules of the magnetic material try to align themselves in direction of external magnetic field, and then this medium is magnetized. This medium now gets some magnetic moment, and the magnetic moment divided by volume or magnetic moment per unit volume is called intensity of magnetization. So here we get some magnetization. Who generates this magnetization? If we don't make the current to flow, the material will be not magnetized. If current is flowing, the material is magnetized. Okay. So actually what we observe is the magnetization occurred, or magnetization happened in the magnetic material is proportional to the H field created by current. So this magnetization vector is proportional to the H field created by this current. Okay. So actually we place a constant of proportionality. This is called chi. Chi. It is pronounced like chi, and it is called magnetic susceptibility. If magnetic susceptibility is more, the material is magnetized more. If it is less, the material is magnetized less. So it tells you the property of medium, that how easily it can be magnetized. If it is large, it can be magnetized at a greater level. So remember, this is called susceptibility. Okay. Okay. So as we have studied susceptibility, now let me tell you the real formula relating magnetic field and susceptibility. Okay. Let me take the reference of this. Actually what happened, the current produced H field. Remember, the current produced H field. So current is the cause for H vector. Then when H vector is created, the material got magnetized. So the H is the cause for magnetization. H is the cause for magnetization. And when magnetized material placed in H field exists, there exists a net magnetic field. So let me tell you the real formula. Actually, first we say we put, or we applied some H field. Okay. Then because of H, magnetization happened. Okay. Magnetization happened. So this is the field we applied. This is the field which got created inside material. So if we add them, it becomes the net something or net influence inside the medium. And if this net influence is multiplied by permeability of free space, this gives us the net B field. Okay, the net B field. The B field can also be written as mu naught H vector, and as we know, the M is proportional to H. So we can write it as chi, or susceptibility, times H, and this becomes B equals mu naught 1 plus chi H. Okay. As we also know that B vector is equal to mu naught times relative permeability times H vector. So by comparison, I think you can easily see that relative permeability is related to susceptibility as 1 plus chi. The relative permeability is related to susceptibility as 1 plus chi. If you know chi, add 1 to it, you get the permeability or relative permeability of that medium. Okay. So let's look at this problem first. This says an iron rod of volume almost 10 to the power minus 3 meter cube and relative permeability 1000 is placed in a core in a solenoid with 10 turns per centimeter and current of 0.5 ampere is passing through the solenoid. Then what is the magnetic moment of the rod? Okay. What is the magnetic moment of the rod? See, if we try to find the H vector or the magnitude of H, H is given by number of turns per unit length multiplied by the current. So as the number of turns are 10 turns per centimeter Per meter they will be 1000 and current is 0.5. So 1000 times 0.5 is 500. This is equal to H. The unit for H is ampere per meter. Ampere per meter. This H creates magnetization. Remember, this H creates magnetization, and magnetization is equal to the chi times H. Okay. What is chi? I think you remember the relative permeability equals to 1 plus chi. So chi is mu r minus 1. So as we are given that the relative permeability as 1000, we have chi as 1000 minus 1, that is 999 times H. H is 500. This is intensity of magnetization, and this intensity of magnetization is actually equal to the dipole moment, the net magnetic dipole moment divided by volume. So we can write it as the mu divided by volume, which is 10 to the power minus 3. Yes. Now if we calculate mu, it will be nearly 499.5 ampere meter square. And if you look closely at all the options, you will find it is the best match with 500. Okay. So obviously B is your perfect choice. Over to next concept. So now we are studying about magnetic materials. So actually magnetic materials, based on their properties, are categorized in 3 parts. And the first classification is paramagnetism. Actually, the example we took in the beginning, it was actually the example of paramagnetism. The paramagnetic substances, the molecules of paramagnetic substances have their atoms, or you can say have their intrinsic dipole moment. Every molecule of paramagnetic substance is a tiny magnet. It has its dipole moment. But if we take a freshly prepared paramagnetic substance, the net dipole moment is 0, as each dipole is oriented in random direction. But when we apply a magnetic field, they try to align along the magnetic field. When they try to align along the magnetic field, magnetization happens. The magnet becomes, the material becomes a magnet, and this is the paramagnetic substance. So what is the paramagnetic substance? Let me explain the properties. The molecules of paramagnetic substances have intrinsic dipole moment, means they have their own dipole moment. They have positive susceptibility, means when H is applied, the magnetization occurs. The magnetization occurs, and direction of magnetization is in the direction of H. So they have positive susceptibility. The magnetization, the direction of magnetization is in the direction of applied H field, and that is because we have positive susceptibility. Okay. More than one relative permeability. Okay. As you know, the mu r is equal to 1 plus x. If x is positive, obviously the relative permeability will be more than 1. Net magnetic field inside is larger than applied magnetic field. Yes, obviously, as magnetization that is occurring inside material is in the direction of H field, the net field would be larger than applied magnetic field. Okay. And if we place such material in the direction or near a magnetic field, they will be attracted towards magnetic field. They will be attracted towards the region of high magnetic field because of this nature. But the attraction is not that strong, as the susceptibility is positive, but it is very less. It is positive, but very, very less than 1. So you can say they are magnetized, but not that very strong. So they are attracted towards the region of higher magnetic field. And then obviously the property, that is paramagnetism, depends upon temperature, because it is affected by random motion. If you increase the temperature, Yes, if you increase the temperature, what happens? The random motion of molecules is increased. Their thermal energy is increased and their alignment will get weaker. If alignment gets weaker, the magnetization weakens. That is why the property paramagnetism depends upon temperature. So their susceptibility is actually a function of temperature. Let me write is function of temperature. How it depends upon temperature, that I'll explain a few moments later in Curies Law. Now let us study the next type of magnetic materials, the ferromagnetic materials, and the property is called ferromagnetism. The molecules of this type of magnetic materials also have their intrinsic dipole moment. So their molecules also behave like a tiny magnet, but they have a special property. What they do, they form tiny regions, and every region, magically, all molecules magnetic moment are in same direction. We take some other region, all molecules will be having their magnetic moment in same direction. These tiny regions are called domains. And if you want to understand how domains are formed, you will have to study quantum mechanics. So we will not be learning quantum mechanics here. Just believe this, that the domain structure is formed. Okay. So if we add magnetic moments of all domains, we still get net magnetic moment as 0, because the direction of domain's magnetic dipole moment is also randomly oriented. Okay. But when we apply some magnetic field across the ferromagnetic materials, the domains having their magnetic moment in the direction of applied magnetic field, they grow their size a lot, or you can say the lots of domains align their magnetic moment in the direction of applied magnetic field, and we again have a lot of magnetization occurring here, a lot of magnetization. The story is a little similar to paramagnetism, but this time the magnetization that occurs is much larger than as compared to what we obtained in paramagnetism. Okay, so here we have domain structure. It has again also a very positive and very high susceptibility. Here we have a very high susceptibility, very high relative permeability, right? And the net magnetic field inside is very, or you can say much larger than the external magnetic field. And when they are placed in magnetic fields, they are very strongly attracted towards region of higher magnetic fields. Okay, so here we have susceptibility very high, positive, and much larger than 1. If we have positive and very larger than 1 susceptibility, we have permeability, relative permeability also 1 plus chi, and it is also very large. So therefore, if we apply some H field here, we get magnetization much larger than H, as chi is very large, and sometimes this chi is of the order of few thousand, like 3,000, 4,000. So if you apply some magnetic field, we get magnetization more than 1,000 times in that ferromagnetic substance. Okay, so this is about ferromagnetism. And the third magnetic material or property is diamagnetism. Actually, let me tell you about diamagnetism. It is present in every material. It is also present in ferromagnetic materials. It is also present in paramagnetic substances, but it is a very weak effect. So if any of the property like ferromagnetism or paramagnetism exists, its effect becomes much weak to you can say, to take into account. But in diamagnetic substance, we do not have their molecules magnetic moment. So here in diamagnetic substances, molecules do not have their intrinsic dipole moment. So the materials which do not have paramagnetism, which do not have ferromagnetism, means their molecules do not have their own dipole moment, show diamagnetism. What we have here, when we apply some H field across diamagnetic substances, the molecules which do not have dipole moment, magnetic dipole moment, actually the dipole moment in it is induced. The molecules get induced dipole moment. Molecules get induced dipole moment. And because of Lentz's law, by Lentz's law, actually the magnetic moment, or you can say the magnetization induced is in opposite direction with applied magnetic intensity. So M and H, they are anti-parallel. You can say M is parallel or M is in the direction of minus H. So here we have negative susceptibility. In diamagnetism, we have very low but negative susceptibility. Remember, the susceptibility is very low and negative. Very low and negative. Right? If susceptibility is very low and negative, as the relative permeability is equal to 1 plus chi, as chi is less than, you can say less than 0 or negative, we have mu r less than 1. But a very little less than 1. You can say for all practical purposes as x, or you can, as chi is very small, the mu r is approximately equal to 1. Okay, so diamagnetic substances have a tendency that when they are placed near a magnetic field, because of the negative magnetization, they get or they feel a weak repulsion from the regions of high magnetic field. Remember this. This effect is not dependent upon temperature. Okay, because this happens in molecules and this has no effect with the thermal energy of molecules. It is an induced magnetic dipole moment, and the induced dipole moment does not depend upon the thermal energy of molecules. So this effect is independent of temperature. Okay, so this is about diamagnetic substances. Copper is a very good example of diamagnetic substances. Okay, so let us understand this question. Here we have a perfectly diamagnetic. Try to notice the word perfectly diamagnetic sphere. So if we have a perfectly diamagnetic sphere and it has a tiny spherical cavity at its center, and this cavity is filled with paramagnetic substance, the whole system is placed in uniform magnetic field B. So this system is placed in external magnetic field B. What happens here? The diamagnetic substance induces, or it gets some magnetization induced in the opposite direction. It gets some magnetization induced in opposite direction. Suppose we apply H outside, we get magnetization induced in opposite direction. And as they are saying, the diamagnetic substance is a perfect diamagnetic sphere. So as it is a perfect diamagnetic sphere, the magnetization will completely cancel the outside H field. And if magnetization completely cancels outside field, the magnetic field inside is 0, because I think you remember B is equal to mu naught times H plus M. Yes. Here we have H and M are in opposite direction, and because it is a perfect diamagnetic substance, the M 100% or M cancels H completely. So we have net magnetic field 0 here. So at the place where paramagnetic substance is placed, we have 0 magnetic field in outer region. And if the paramagnetic substance is placed in 0 magnetic field, there will be no magnetization of paramagnetic substance. There will be no magnetic field here. So net magnetic field at the paramagnetic substance will be 0. Okay, so that was your question. Next, now we have a paramagnetic substance in the form of a cube whose sides are 1 centimeter, and it has a dipole moment of 20 times 10 to the power minus 6 joule by Tesla. When a magnetic intensity, means H field, of this much ampere per meter is applied, is magnetic susceptibility. They are asking us magnetic susceptibility. I think this question is very simple. As you know, the M is equal to chi times H. They are asking us susceptibility, that is chi. Okay. As the M vector or the magnetization is net dipole moment divided by volume, we have net dipole moment as 20 times 10 to the power minus 6 divided by volume. We have volume as 1 centimeter cube. As the edge has 1 centimeter, the cube's edge are 1 centimeter, the volume will be 1 centimeter cube. But in meter cube, we have 10 to the power minus 6 meter cube equals chi times H. And H is actually 60 multiplied by 10 to the power 3. These got cancelled, and now we have H, and you solve this, chi, and the value of chi will be nearly 3.3 times 10 to the power minus 4. So D is your perfect choice. Yes, now we will understand Curies law. I think few minutes back I told you that the paramagnetism depends upon temperature. When temperature is raised, the thermal energy is increased. And when thermal energy increases, magnetization decreases. So actually, the Curie found that the susceptibility of paramagnetic substances, paramagnetic substances depends upon temperature, and Curie found that the susceptibility of paramagnetic substance is inversely proportional to absolute temperature. So she gave a law that susceptibility equals some constant divided by T. You raise the temperature, the susceptibility decreases. Okay, and the C is called Curie's constant. C is called Curie's constant. So remember, this law is about paramagnetic substances, and when the temperature, the absolute temperature increases, the susceptibility decreases because of randomization, increased randomization of molecules because of thermal energy. We also notice that temperature has its effect on ferromagnetism also. Let us see how. Suppose we have a ferromagnetic substance and we raise the temperature, almost nothing happens to its magnetic properties. But if we keep on increasing the temperature, we see that at a fixed critical temperature for every medium, for every material, its domain structure is gone. The molecules have so much thermal energy that they destroy the domain structure. So critical temperature for ferromagnetic substance at critical temperature, let's say Tc is critical temperature, at, or let's not say at, above Tc, above critical temperature Tc, the domain structure is destroyed. Domain structure is destroyed. When domain structure is destroyed, you can say the ferromagnetic substance becomes paramagnetic. Ferromagnetic substance becomes paramagnetic. And when it becomes paramagnetic, it starts following Curies law. So for this type of medium, this type of material, the Curies law is given as the susceptibility is equal to some new constant C dash divided by T minus Tc. T minus Tc. Remember, this happens at a temperature above Tc. So we have T minus Tc here. Okay. So this law is followed when the temperature is more than critical temperature. Otherwise, if a ferromagnetic substance has temperature less than critical temperature, this has no meaning there. Let us see what we have next. We now have a paramagnetic material and it has this much atoms per meter cube. Its magnetic susceptibility at temperature 350 Kelvin is 2.5 times this. What is susceptibility at 300 Kelvin? I think this question is very simple. As you know, the paramagnetic material susceptibility is equal to C divided by T. So susceptibility is inversely proportional to absolute temperature. So we can say the multiplication chi times T is constant. So we have chi as 2.8 times 10 to the power minus 4 multiplied by temperature, which is 350, equals to new susceptibility at new temperature time new temperature is 300. If you solve for chi dash, you will find approximately A as correct answer. Okay. So in this question, we have a paramagnetic substance and whose magnetization is 6 ampere per meter, where it is placed in external magnetic field of 0.4 Tesla, and that too at a temperature of 4 Kelvin. And when it is placed in some other magnetic field at some other temperature, what is the magnetization? So here they are changing the external magnetic field also, and they are also changing the temperature. So susceptibility is also changing. So let me handle this. As you know, the external magnetic field is equal to mu naught times mu r times h. This collectively is called the net permeability, or you can call it as mu. So let me write B as mu times h, and h can be written as, how h can be written as, we can write h as m divided by chi, because the m is equal to chi times h, so we have h as m divided by chi. And according to Curies law, the chi can be written as some constant divided by absolute temperature. So we have B equals mu times m times divided by C times absolute temperature. So we are changing magnetic field, the magnetization is changing and the temperature is changing. So we have mu and C constant. So we can write the B1 by B2 equals M1 by M2 multiplied by T1 by T2. So here M2 becomes M1 T1. What is M1? M1 is 6. The T1 is 4 Kelvin. No, yes, it is 4 Kelvin divided by T2 is 24 Kelvin, and we also have B2 here. So B2 is 0.3 Tesla and B1 is 0.4 Tesla. So this comes out to be 0.75 ampere per meter. So option D is your correct choice. Now we will learn the relationship between magnetization vector and H field for magnetic, or you can say for ferromagnetic substances. In case of paramagnetism, they were proportional, but here they are not proportional. So to understand this, let us take example that we have a solenoid where we can send a current I, and suppose the current I can be varied. When I is passed, the H is created. H is equal to number of turns per unit length times I. Suppose initially the current is 0, so H is 0, and here we place a fresh ferromagnetic substance like iron, and the net magnetization in the iron is 0. So we have H0 and M0. Now when we slowly increase current, the H field is produced. The domains of the ferromagnetic substance, they try to align themselves in the direction of H field. The M vector is induced or produced, and what we see that M and H are not linearly dependent. They have a non-linear relationship like this. And when current is increased beyond a certain limit, the magnetization now does not increase. Why? Because when all the atoms have their dipole moment aligned in external field, now magnetization cannot increase because every molecule is aligned. So we say the magnetization has a saturation level. This is saturation level. Now suppose we start decreasing the current. When we start decreasing the current, H is reduced, M is also reduced, magnet starts demagnetizing, but when we keep or when we make the current 0, the H field becomes 0, but still what we observe that few domains or few molecules stay aligned with the old direction of magnetic field, and we have some magnetization left in the material. This property that of memory, you can say this property of memory, or this property that the flux or the magnetic field or the magnetization that remains inside material is called hysteresis. It reminds us that we have applied some magnetic field and now that is made 0, but still we see the some magnetization is left. This is called retentivity. If now we want to make the net magnetization 0, we will have to apply some opposite H field. And by applying opposite H field, means applying H field in opposite direction, now it tries to demagnetize the material in opposite direction, and then if we have negative current, the M decreases, and the value or the negative value of H when M decreases to 0 is called coercivity. Now if we keep on increasing the current in negative direction, this material is magnetized in opposite direction, and it again is again saturated in negative direction. And now if we make the current 0 again in negative direction, we again see some magnetization is left, which is retentivity. Okay. Now a positive current, a positive field again makes the net M 0, and when we make the current positive again, it saturates at some level. Now if we keep on increasing current in positive direction, decreasing to 0, then increasing the current in negative direction and decreasing to zero, and we keep this cycle on and on, this loop is followed. This loop is followed. And this loop is called hysteresis loop. This loop is called hysteresis loop. As you know, M is roughly proportional to magnetic field, as magnetic field equals to mu naught times H plus M. In ferromagnetism, M is very, very large as compared to H. You can say the B is nearly equal to mu naught times M. So we can also say this graph as B, and B is depending upon H like this. So this curve is also called BH curve. If retentivity is large, understand, if retentivity is large, it means if you magnetize it in certain direction and make the external effect zero, a large magnetism is retained inside that material. And this property is very important for making permanent magnets, because in case of permanent magnets, we magnetize it once and then they are magnetized forever. Okay, so for making permanent magnets, we need larger retentivity and also larger corrosivity, because what we also want that it cannot be demagnetized very easily. So if corrosivity is large, it will not be demagnetized very easily or for very small currents. So for making permanent magnets, we must have large retentivity and large corrosivity. For permanent magnets, we must have large retentivity. Say retentivity is represented by R, and large corrosivity, which is represented by C. Okay. Actually, when these things are large, when these corrosivity and retentivity are large, the area of loop is big, and actually the loop area is proportional to losses. When we keep on magnetizing, demagnetizing material, it repeatedly, the magnetic substance is repeatedly magnetized and demagnetized, and that creates a lot of heat losses, and that heat losses are proportional to the loop area. So bigger is the area, bigger are the loop losses, or they are also called hysteresis losses. Okay. So in case of permanent magnets, we have to magnetize it once and then the external effects are removed, so we are not much worried about the losses. But suppose we want to make electromagnets, we want to make core of a transformer, we want to make core of a generator, where the variable currents flow and the currents keep on varying forever. If currents keep on varying forever, the material inside them will keep on magnetizing and demagnetizing forever. Okay. And if the loop area is large, it will create a large heat losses. So for making transformer or electromagnets, we want the material with a very small loop area. And if loop area will be small, the retentivity and corrosivity will be close to origin, that they too will be small. So remember, for transformers, core, also valid for electromagnets, also valid for generator or motors. For core of transformer or any alternating instrument which always performs some operation, we must have a small retentivity and corrosivity. So remember this rule or loop, and let us see few problems based on this. So here we are given that a BH loop, right? and it gives you some values. Now they are asking what is the retentivity, corrosivity and saturation. Okay, so if we see, saturation happens here, and if you clearly see, this says the saturation magnetism is actually 1.5 Tesla. So 1.5 Tesla is saturation magnetic field, and that is in option A and option B. So we have 1.5 Tesla as saturation magnetic field. If we talk about the retentivity, see, this point is called retentivity, and retentivity is actually 1 Tesla. So retentivity is 1 Tesla, and corrosivity. So corrosivity is actually minus 50, or you can say in magnitude it is 50 ampere per meter. So they are asking us retentivity, corrosivity and saturation values. So retentivity is 1 Tesla. Let us see where is 1 Tesla. So we have in option D 1 Tesla. In place of corrosivity we have 50 ampere per meter, and saturation magnetic field is 1.5 Tesla. So we have D as perfect choice. Next question. Here we have a bar magnet, and it is demagnetized by inserting it inside a solenoid of length 0.2 meter, 100 turns, and carrying a current of 5.2 ampere. What is the corrosivity of bar magnet? See, if the bar magnet is completely demagnetized, it means that the corrosivity is, or the H vector is equal to corrosivity. Okay, because you know, if H is equal to corrosivity, the magnetization is 0. So it will be completely magnetized when H equals to corrosivity. Yes. So we have been asked what is corrosivity of the bar magnet, and corrosivity is equal to H, and which is equal to N times I. Okay, what is N equal to? N is number of turns per unit length. We have 100 turns per 0.2 meter. So we have 100 divided by 0.2 as number of turns per unit length, and multiplied by current, and current is 5.2 ampere. So you multiply these two and you will have 2600 ampere per meter, and that is why B is your correct choice. Next question. Now they are saying magnetic materials used for making permanent magnets and magnets in transformer have different properties. I think you understand this. And for making permanent magnets, the area of hysteresis loop must be large. It must have large corrosivity and retentivity, and for transformers it must have small corrosivity and retentivity. So if we check our options, we must have, for transformer we must have small corrosivity and retentivity. For permanent magnets we must have large corrosivity and retentivity. So A option says large, small, small, large, large, large. Yes. For making transformers we must have small retentivity and corrosivity. So this is also wrong. For making permanent magnets we must have large retentivity and large corrosivity. So obviously option D is correct. Next. Here we are given that a BH curve for ferromagnet is shown in the figure. The ferromagnet is placed inside a long solenoid. Okay, so we have a long solenoid with 1000 turns per centimeter. If we have a 1000 turns per centimeter, we will be having 10 to the power 5 turns per meter. And they are saying that, please check the corrosivity. The corrosivity is 100. See. And they are saying the magnet is completely demagnetized when we place it inside solenoid. Means the H field developed inside solenoid is equal to corrosivity. So corrosivity is equal to 100, and that is equal to N times I. As N equals to 10 to the power 5 equals to 100 times I, we have I as 10 to the power minus 3 ampere, that is 1 milliampere. So B is your perfect choice. Again, we have a similar question. It says hysteresis loop for two magnetic materials A and B are given below. Can you see one has a bigger area and one has a smaller area? So the bigger area is used for making permanent magnets. I think you have studied this a few minutes back. I told you this. And the loop with the smaller area are used for making transformer and electromagnets and generator cores, etc. So if we check the options, we will be having A for transformer. Never. It has a very strong, very large hysteresis losses. So A, this is wrong. B for electromagnets. Okay, B for electromagnet is fine, and transformer, obviously. B has a smaller area, so B must be used for making electromagnets, because these electromagnets and transformer core are very frequently magnetized and demagnetized, and high losses we cannot tolerate in these cases. So we have B, perfect choice for making transformers and electromagnets. Now we will study what are alternating currents or alternating voltages. See, if alternating current or voltage alternate, or you can say change their directions in fixed interval of time, okay, and repeat its shape, then we say the values are alternating. Okay. Like in the first example, we can see the current is positive for a certain interval of time, then it is equally negative for the equal interval of time, then it is again positive. If we continue the graph, it will again be negative, it will again be positive. So the shape of the current is repetitive and it is repeating after a certain interval of time, then we say the current is alternating. Okay. Remember, the shape here is a sine wave shape, therefore we call it a sinusoidal AC. Okay, but the shape is a triangular type, we call it a triangular pulse AC, or if it is a square or rectangular type, we call it a square pulse AC. But one thing is common, okay, the direction is changing in fixed interval of time. So here also we see positive for some time and equally negative for some time, then again positive for some time and equally negative for another time. So the main important condition is current or voltage should alternate their directions in fixed interval of time, and the net average of any alternating quantity must be 0. So if current or voltage I or V is AC, means alternating, the average must be 0. The average over a full cycle must be 0. Its average, current's average over full cycle must be 0. What is the cycle? When current starts repeating its shape, we say it's a full cycle. So can you see from here to here, there is a one cycle, and after it the currents start repeating its shape. So it is one cycle, and obviously one can see for this much period of time the current is positive, for this much equal period of time the current is equally negative, so its average is definitely 0. In triangular pulse AC also we have positive and negative. So for one cycle the average is 0. Here also for one cycle average is 0. So if a alternating quantity has its average over a cycle is 0, then we say it alternating, but also it must repeat its shape continuously. Okay. So this was all about definition of alternating current. Let's move a little. So we will now understand how we produce alternating currents. Actually, out of these three, the most important waveform or the most important shape is sinusoidal, because the generation of sinusoidal AC is simple. And now we will understand how we generate alternating voltages or alternating current. So for this I have here a simple diagram of a generator. Okay. So suppose we have two magnets, one is a north pole and other is a south pole. They may be two independent magnets or just two poles of a single magnet, doesn't matter. And between them we have a magnetic field from north pole to south pole. Can you see? Okay, the magnetic field may be variable, but I have drawn it almost uniform for the sake of simplicity. Now we have a coil. Can you see this green coil? It is a coil, let's say having some certain number of turns in it. And what we do, we rotate this coil, say at some constant angular speed omega. Okay. If we let the magnetic field's value is B, the area of coil as A, and number of turns in the coil as N, then the flux linked or the flux linkage through the coil will be N, B, A. I think you remember the area can also be taken as a vector quantity, and the area vector will be directed perpendicular to the coil's plane, and that is area vector A. But when we turn the coil with constant angular velocity, after a time t, the plane of coil will turn by an angle omega t, and after turning, the coil's plane would look like something this, and the area vector will too turn by an equal angle theta. As the constant angular velocity omega, so theta must be equal to omega times t. So if there is an angle between magnetic field and area vector, and that angle is omega t, the flux will be written as NBA cos omega t. So can you see? We have generated flux through the coil, and that is varying alternately with a function of cos omega t. According to Faraday's law, the induced EMF is equal to negative of d psi by dt. So if we differentiate this flux linkage with respect to time, we would get N B A omega sine omega. So we now have alternating voltage. And the maximum value of alternating voltage can be written as NBA omega. This can be called as maximum value of alternating voltage, and the voltage can be written as equals to E naught sine omega t. So that is how we generate alternating voltage. And if we connect a resistor or capacitor or inductor in this path at the ends of this coil, obviously the alternating voltage will send alternating current in those elements. Okay, so this is how we generate alternating voltages. Okay. So I think you remember how we used to represent DC sources or batteries. The symbols for DC batteries were either this or this. But as in alternating voltage sources, we do not have fixed polarity. The polarity is flipping. Sometimes the left end is positive, sometimes the right end is positive. So as we do not have the fixed polarity, we don't write the plus and minus sign as we used to write in DC. Here we show AC source like this, circle, and in that a wave like shape, and this represents an AC source. Always remember, if you see this, always understand this as an AC source. Okay. Now we will understand the average value. As alternating quantities are equally positive and equally negative for fixed interval of time, if you calculate the full cycle average of any AC quantity is always 0, because it is equally positive and equally negative for equal interval of time. Like, can you see here, it is positive here, it is negative here, so average is 0. But how we calculate average? Let me tell you first. Suppose you have a quantity f as a function of time, and you want to find its average in a given interval of time. So if you want to find the average of function f let's say from 0 to t, obviously the average is always calculated in a fixed interval of time. The average value can be written as ft dt from 0 to t. So you integrate ft dt divided by the time interval t. This is the value of average. So this is how you calculate the average value. So if you calculate average value for full cycle, it will definitely come out to be 0. But if you calculate the half cycle average, suppose the time period or the period of the wave is t is period, and if you try to calculate the half cycle average, means average from 0 to t by 2, you will have to integrate the function from 0 to t by 2, and then if you have a sinusoidal wave, remember, if you have a sinusoidal wave, the average is nearly 2 by pi times of the peak value. So suppose the peak value is 1 here, suppose the peak value or the maximum value is 1 here, the average value will be 2 by pi. Always remember, if peak value is other than 1 like k, then the average value will be 2 by pi times k. If we have a triangular pulse with maximum value as 1 or the peak value as 1, then the average would be 1 by 2 times of peak value, that is 1 by 2. If we have a square wave, okay, if we have a square wave of peak value 1, then we will be having average over half cycle as 1, as can be easily seen. Okay, so always remember this, these three shapes. If you have a sinusoidal wave, whether sine wave or cos wave, doesn't matter. If you have a sinusoidal wave, then half cycle average is 2 by pi of peak value. For triangular wave, you have half of peak value, and for a square wave, you have equal to peak value, the half cycle average. But the full cycle average is always 0. Now we will understand the RMS values. RMS values in alternating circuits are very important, and they are said to be the effective values. They are said to be the effective values. So what is the meaning of RMS? The meaning of RMS is root of mean of squares. Root of mean of squares or root of average of squares. So suppose you have a function ft and you want to calculate its RMS value from 0 to t. So the value of RMS is actually root of mean of squares. So if we square it and then take mean, that is average, so average would be integral f square dt from 0 to t and divided by t. So this is mean of squares, and then you take square root. This becomes RMS value of that function for the specified period of time. Okay, so if you have a sinusoidal wave, please remember this. If you have a sinusoidal wave, just take one example as I equals to I naught sine omega t and put the value here. Okay, put the value here. So if you have a sinusoidal wave, its RMS value for full cycle would be 1 by root 2. Here it would not be 0 because we are squaring it. So negative pulses become positive when we square them. Okay, so remember this point. The sinusoidal waves have their RMS value as 1 by root 2. The triangular pulses have their RMS value as 1 by root 3, and square pulses have their RMS value as 1. So RMS values are important, are very important, because they are called the effective values in alternating circuits. They will produce the same, the RMS values in fact produce the same effect as an equal DC value would create. Okay, so always remember this point. And next, let us understand, actually the domestic supply that we have in our homes is 220 volts 50 hertz. It's 220 volt 50 hertz. So if at some place it is written that the voltage is 220 volt 50 hertz, always remember in this type of notation, we are always given RMS values or effective values. So 220 volt is actually the RMS value, not its peak value. If you want to find the peak value, so I think you remember, actually the RMS value was peak value divided by root 2 for sine wave. For sinusoidal wave, the RMS value was peak value divided by root 2. So peak value would be RMS times root 2. So here for this type of voltage, we have peak value as 220 root 2 volt. And 50 hertz indicates that there are 50 cycles. There are 50 cycles of the quantity in 1 second. So it is just the frequency of changes. Okay. Mostly we see two type of symbols for AC. As I explained you, that this is the symbol for AC voltage. But if some time below this, it is written that 200 volt 50 hertz. So here we have to understand that the RMS value would be 200 volt. The peak value would be 200 root 2 volt. And the frequency of the signal is 50 hertz. Means there are 50 cycles in 1 second of that signal. But if it is written that or they write it as V equals to 200 sine omega t or 100 pi t. Okay. So if at some place they are giving you the voltage like this, they are giving you the exact function, exact sinusoidal function, then remember here this 200 would be actually the peak value. This 200 is peak value. If it is written with function, you can easily see the maximum value of sine theta is 1. So maximum value of voltage would be 200, and 100 pi is actually omega. Omega is angular frequency, which is equal to actually 2 pi f. So obviously f equals to omega upon 2 pi, that is 50 hertz. So there are two ways in which they can give you the values of voltage. One is this and one is this. If simply voltage and frequency is written, we have voltage as RMS value, remember this. And if we have a complete function, then we have a peak value here. Okay. So now it's time to understand the AC circuits. When we apply resistance, capacitance and inductors or any combination of these across an alternating voltage source, obviously alternating current flows through them. Okay, and solving that alternating current is the purpose of AC circuits. Okay, so first we will understand the individual behavior of resistance, capacitance and inductors in AC circuits, and then we will understand their combinations. Okay, so let me first put simply a resistance across a AC voltage source. Okay, and the AC voltage source is given by V naught sine omega t. So V naught is actually its peak value and omega is its angular frequency. Remember, omega is angular frequency. From omega you can find the frequency, and the frequency would be omega upon 2 pi. Okay, so when we apply some voltage across resistance, the resistance always follows Ohm's law. And Ohm's law says the instantaneous current in the resistance is equal to the instantaneous voltage upon resistance. So if by small v we represent instantaneous voltage, let us put instantaneous voltage here, we can get V naught by R sine omega t. If you think of the maximum value of current, obviously the maximum value of current is this coefficient V naught by R. You can write V naught by R is I max or I naught. So I becomes I naught sine omega t. I think you remember this angle or this thing after sine, that is omega t, is called phase of the quantity. So if you check the phase of voltage, it is omega t, and if you check the phase of current, it is also omega t. The both functions are same. So if you think of the difference of phase, actually the phase difference is 0. Phase difference between voltage and current is 0 because the phases are same. If phases are same, if you try to draw the voltages plot, if it is like this is maximum voltage and voltage. The currents waveform would also follow the same pattern, only the maximum value would be different, and maximum value is I naught, and it is equal to actually V naught by R. The magnitude of current would be less than the magnitude of V naught if R is more than 1 ohm, obviously. Okay. So as the phase difference is 0, the both follow same kind of waveform. They are both positive together, negative together, and 0 together. They both are maximum together and minimum together. Okay. So that is the actually meaning of phase difference. Okay. We can also show this phase relationship by a technique called phasor. And phasor technique involves a few imaginary rotating vectors. Okay. So what are phasors? If you just look at the voltage value, it is V equals to V naught sine omega t. It is V naught sine omega t. So if you draw a vector whose magnitude is equal to the maximum value V naught, and assume this vector to be rotating with angular velocity equal to angular frequency of the signal omega. Okay, angular frequency. Then its projection on this axis, would actually represent the instantaneous value of the voltage. Like suppose it turns by some angle omega t. After some time it turns by an angle omega t. If you look at its projection, obviously this would be, according to trigonometry, this would be V naught sine omega t, and that is obviously the value of instantaneous voltage. You can check. A small v is V naught sine omega t. So actually the projection of phasor represents what? Instantaneous values. Okay. So if we have to draw current and voltage together, the phasor of voltage would look like something like this, V naught. Okay. Please imagine this as a rotating vector, and as there is no phase difference between current and voltage, the phase of both is same, the phasor of current would overlap on this. There will be no angle between them. The phasor of current will overlap on this, and this represents the phasor, the combined phasor of voltage and current. Always remember, the length of the vector should be equal to the maximum value of the alternating quantity, and the phase difference between two is 0, so that is why they are overlapping. Okay. Let me tell you, or let me discuss a question based on this. Here they say we have an alternating voltage 220 sine 100 pi t volt is applied across a purely resistive circuit. Okay, and the resistive load is 50 ohm. What is the time taken for the current to rise from half of the peak value to the peak value? See, actually, if we plot the voltage, it would be a sine wave. And as in resistive circuit, we have no phase difference between sine wave and voltage wave. So the current wave can also be drawn like this. Okay. The maximum value of current I naught is actually equals to V naught by R, and which can easily be calculated. V naught is 220 and R is 50, but that is not needed here. On this axis, actually we have theta. On this axis we have theta. And what is theta? The theta is actually 100 pi t. So theta is 100 pi t. Remember, I think you know the maximum value of sine theta is at pi by 2. And its value would be half of peak value at pi by 6. Here we get I naught by 2 at pi by 6, because I think you remember the sine pi by 6 is 1 by 2. Okay, so at sine pi by 6 we have the value of current as I naught by 2, because sine theta is 1 by 2. So the difference of angle or difference of phase between these 2 points is delta theta, and if you calculate delta theta would be 100 pi delta t, and this will be equal to pi by 2 minus pi by 6, that will be pi by 3. Cancel pi and you will have delta t as 1 by 300 second multiply by 1000 in numerator and denominator, and you will have 3.3 millisecond. So D is your correct choice. So now we know how a resistor behaves in alternating circuit. Suppose we have a pure capacitor. Pure capacitor means there is no resistance in it. Okay, we have a pure capacitor and we apply this capacitor across a alternating voltage. I think you remember, by fundamentals of capacitor, the charge on capacitor is equal to the capacitance times the voltage across it. So this is the value of instantaneous charge on capacitor, and it is equal to the capacitance times the voltage across it. And if you want to find current in capacitor, the current can be written as rate of change of charge, that is dq by dt, and it would be C times dV by dt, as C is a constant. If you differentiate the voltage, you would get omega C V naught and cos omega t. Omega C V naught and cos omega t. This can be rewritten as V naught divided by 1 by omega C and sine omega t plus pi by 2. By this, you can see this is the formula similar to V naught by some quantity, and this quantity, according to units, this quantity must be having the units of resistance. Okay, so this is actually a quantity 1 upon omega C, and it is the, you can call it as the resistance offered by capacitance to AC current, the resistance offered by capacitance to AC currents, and this quantity here is called reactance X. As the reactance is of a capacitor, it is called capacitive reactance. Okay, let me write it as capacitive reactance. As the current is depending upon cos omega t, we can write it as sin omega t plus pi by 2. So these two functions are similar now. And if you check closely, we have phase omega t in voltage and omega t plus pi by 2 in current. So what we say in terms of phase, current is leading the voltage by 90 degrees or pi by 2. The current leads voltage by 90 degree in pure capacitance. This quantity V naught by XC, V naught XC is obviously the maximum value of current. So we can write the current as I naught sine omega t plus pi by 2. So this is the formula for current, and current, if we have omega t plus some angle, we say current is leading. We say current is leading. Okay. And if we try to draw the waveforms, if voltage has waveform like this, okay, voltage has waveform like this, the maximum is V naught. The current's waveform would be 90 degree shifted backward because it is leading. So current's waveform is something like this. And the maximum current is actually I naught, which is equal to V naught divided by the capacitive reactance. Always remember this point. Okay. So this is about the waveform. And if you try to draw the phasor, the phasor of voltage is V naught, but as the current leads voltage by 90 degree, if it is leading, always make it ahead in anti-clockwise direction. So make current phasor 90 degree ahead in anti-clockwise direction than voltage. This will be the phasor of current and voltage for purely capacitive circuit. And this is a very important line. You all should remember that in pure capacitor, current leads voltage by 90 degree or voltage lags current by 90 degree. Okay. Next, or now we will understand the behavior of inductor. The behavior of inductor in AC circuits. So we have applied a pure inductor. So it is a purely inductive circuit. The pure means we have no resistance in the coil. We have no resistance anywhere in the windings. So we have a pure inductor L across a voltage. And if we write KVL, I think you remember the V minus L di by dt, as we used to do in LR circuits or LC inductor circuits. This is equal to 0 because we have only two elements, the voltage minus L di by dt equals to 0. So you can write it here as di is equal to 1 upon L and V dt. If you integrate this, you will get current as minus V naught by omega L and cos omega t, and as it is an indefinite integration, we can add a constant, say k. Now we will understand it, how to find the value of k. See, this is purely an alternating quantity because it has cos omega in it. So if you calculate the average, its average is 0. As current is also an AC current, so its average too should be 0. And if its average is 0, this term's average is 0, its average must too be 0. But if a quantity is constant, think of it, if a quantity is constant, its average can be 0 only if its value is 0. So that is why from this logic we can say k equals 0. K equals 0. If you check this term V naught by omega L, obviously it is the maximum value of current I naught. Okay, it is the maximum value of current, and if you compare this with V naught by something equals to current, obviously omega L will be having units of resistance. So you can call it as resistance offered by this inductor to AC current. Resistance offered by this inductor to AC current. So this is called actually the reactance. So omega L here is called reactance of inductor, that is inductive reactance. So what is the reactance? You can always imagine it this way, that reactance is actually the resistance offered by capacitor or inductor or combination of both to an AC current. So we can write our current as I naught, and we have minus cos omega t. So minus cos omega t can be written as sine omega t minus pi by 2. Sine omega t minus pi by 2. So if you look at the phases of voltage and current, you find the current is not ahead, current is not leading, but actually current is lagging in phase by 90 degrees. So in inductor, I lags V by 90 degrees, or you can say voltage leads current by 90 degrees. Okay. If we draw the waveform, if the voltage waveform is like this, the current waveform would look like this. The maximum current I naught would be equal to V naught by XL, where XL is omega L. Okay. If we now draw the phasor of voltage can be drawn like this. The first phasor you can draw in any direction, but the current is 90 degree lagging. So if it is lagging, we must draw this in clockwise direction with respect to voltage. This is the phasor of actually the purely inductive circuit. As now you understand, the current and the voltage waveforms may differ in phase. And do you know, this phase difference plays a very important role in power. So we will first understand the power analysis in AC circuits, because actually the power is the core idea of every chapter. So as you know, the instantaneous power, I am representing instantaneous terms by small case letters. So instantaneous power is always instantaneous voltage times instantaneous current. As now we have idea that current and voltage may differ in phase, sometimes positive, sometimes negative. So let us assume the voltage is equal to V naught sine omega t and current as I naught sine omega t, but current is a little different in phase, so we have added a phase phi. Okay. If all parameters like frequency, the voltages, the resistance and the capacitor inductance are kept fixed, we observe that phase difference once obtained will remain constant during the operation of the system. So you can think of this phi as constant for one type of circuit. So if we find instantaneous power, it will be simply multiplication of V times I. So P equals V naught I naught sine omega t plus phi and sine omega t. If you multiply and divide this by 2, you would be having P as V naught I naught by 2, and I think you remember the value of 2 sine A sine B. The value of 2 sine A sine B is cos A minus B. So we have cos A minus B would be phi and minus cos A plus B. So cos A plus B would be 2 omega t plus phi. This is the value of instantaneous power. And the only variable term here is cos 2 omega t. You can notice that the angular frequency of power is not omega, it is 2 omega. So we must remember this thing from here, that if frequency of voltage or current is omega, or the angular frequency of voltage and current is omega, the angular frequency of power will be doubled. Or if frequency is f, the frequency of power will be 2f. Okay, so we can write very important point from here. Frequency of power equals twice of frequency of I or voltage. Now, as the power is varying with a very high frequency, we'll be mostly interested in average power. Okay, so if we calculate the average power, this is a constant V naught I naught by 2. 2 can be written as root 2 times root 2, and see, average of this term, average of this term would be average of first term, that is cos phi, minus average of second term, which is cos 2 omega t plus phi. Now look closely. Actually, cos phi, if phi is a constant, cos phi is also a constant, and the average value of constant term is equal to that constant value. So we have average of cos phi as simply cos phi. And this term is variable. This term is actually varying with time, and it is actually an alternating term. It is positive and negative for equal amount of time. So its average value would be 0. Its average value would be 0, as it has cos 2 omega t. It is variable with time, and if it is variable with time, it will be positive and negative for equal amount of time. So the average is obviously 0. So we have average power. Let's write average power as capital P, and average power would be, see, we have V naught by root 2, I naught by root 2. So you can write V naught by root 2 as V RMS, I naught by root 2 as I RMS, and then we have cos phi. This is the value of average power. You can also say that power is not just equal to effective voltage and effective current. It also has another factor, cos phi, and this factor is very important, okay, in power in AC circuits, and this factor cos phi is popularly known as power factor. If you want to calculate power, the calculation of power factor is very important, and remember, it is equal to cos of angle between current and voltage waveform, or current and voltage phasor. Okay, so if we just go back a little and start from purely resistive circuit and look at the power here. So as the phase difference is 0, we have 0 phase difference between current and voltage. So phi equals 0. If phi equals 0, cos phi equals 1. So always remember, for a purely resistive circuit, power factor is 1. For purely resistive circuit, power factor is 1. Okay, and the power factor is 1, then power becomes simply V RMS I RMS, means effective voltage times effective current. if we have a pure capacitive circuit, can you see the phi equals pi by 2? If phi equals pi by 2, power factor which is equal to cos phi is 0. And if power factor is 0, power is 0. So, the capacitor do not dissipate or do not in fact store average power in it. So, they do not take any average power. In fact, instantaneously in half of the cycle, they take some power, and in the remaining half of the cycle, they deliver the same power back to the source. So, the average power with capacitor is 0. And also in case of inductors, again can you see the power factor is 0 because the angle is 90. So, here also the power factor is 0, and that is why average power is 0. So, inductor 2 takes energy or power from the source in half of the cycle, and the next half cycle it returns it back. So, there is no average power with pure capacitive or pure inductive circuit. Only the resistance dissipates power in AC circuits. Remember this point. This is true when there will be combinations of capacitor resistances and inductors. Only the resistance will dissipate power. So, we have this question where they say a small signal voltage, the voltage is applied across an ideal capacitor. So, what will happen? See, in ideal capacitor, we know the current leads voltage by 90 degree. So, here it is written that lags voltage by 90 degree. It is wrong. Over a full cycle, the capacitor does not consume any energy from the voltage source. That is true. Because power is, the average power is 0. If average power is 0, the net energy in over one cycle would definitely be 0. So, B is the perfect choice. Then they say current is in phase with voltage. That is wrong, because current is in phase with voltage only in case of purely resistive circuit, and current leads voltage by 180 degree. That too is wrong, because current leads voltage but not by 180 degree. Actually, it leads by 90 degrees. So, now as we have studied inductors, capacitors and resistances behavior individually in AC circuits, now we will understand how to handle circuits that contains all three, okay, or any two of them. So, suppose we have a circuit where the inductor, capacitor and resistor are connected in series. We are firstly dealing the series circuit, and these are very important for every exam like boards or NEET or JEE. All exams, mostly they ask about the series circuits. So, in case of series circuit, we start our analysis by drawing phasor, remember. So, if we have voltage as V naught sine omega t, one thing is sure that current here would be alternating, because voltage is alternating, current too will be alternating. I am not drawing any direction of current because the direction of current is flipping. Sometimes it is clockwise and sometimes it is anti-clockwise. So, we have direction of current flipping here. The most important property of a series circuit is the current in each element will be same at every time. So, current is same in every one and voltages will be different. The voltages are divided. Suppose we call the voltage across inductor as VL, voltage across capacitor as VC and voltage across resistor as VR. These voltages with the small letters actually represent the instantaneous values, remember. Okay, so we have five quantities. One, the net voltage, the three voltages and the current. These all are alternating quantities. Okay, and if all these are alternating quantities, they all have their phasors. So, while drawing phasors, let's first assume the current in the circuit is, I'm assuming the current, as I know the current would be alternating, I'm assuming current as I naught. Let us say the maximum current is I naught. I'm assuming the value I naught. Then we have sine omega t. But the current may differ in phase with voltage. And we initially do not know what is the phase difference. So I'm assuming the phase difference to be phi. So I've assumed the current like this. Okay. But after analysis, we will be finding their values. Actually, we have to draw 5 phasor quantities. So first, we should draw a common phasor. And do you know, out of these 5, the current is common in all 3. So you can say the current is a common phasor. So we will first draw a common phasor, and that is current. Its magnitude is not known. So I'm assuming its magnitude is I naught, which is unknown right now. Now the first thing I think you remember is, in purely resistive circuit, current and voltages are in same phase. So if we just think of this tiny circuit, we have current phasor like this, and VR the voltage across it. At least this is a pure resistive circuit. So voltage across resistance will be in phase with current. So we have VR. Let us say VR, capital VR, as the maximum value of instantaneous voltage, small VR. Then I think you remember, in purely capacitive circuit, as this is a purely capacitive circuit. If this is a purely capacitive circuit, in purely capacitive circuit, the current used to lead the voltage by 90 degrees. So voltage automatically lags current by 90 degrees. So I must draw voltage across capacitor like this, right? And in inductor, I think you remember, the current lags voltage, that is, voltage leads current like this. This is VL. So now we have drawn 3 voltages, phasors of 3 voltages, VL, VC and VR, VL, VC and VR. And as there is one small point you should remember, as according to KVL, the sum of these 3 is equal to this. The sum of these 3 instantaneous values must be equal to this net value. In phasors, we say the sum of these 3 phasors, considering them as vectors, will give you the phasor of the voltage, net voltage V. Always remember, if these 3 are adding in instantaneous way and they give you the value of net voltage, instantaneous voltage, their phasors, if added vectorially, they will give you the resultant voltage's phasor. So always remember, if we add these 3 vectorially, you will get the resultant phasor of net voltage, supply voltage V naught. So we have to add these 3 vectors. Okay. Now we will first add these 2 phasors because they are in opposite direction. Actually, which is bigger, VL or VC? It depends upon many factors. Okay. But as they are opposite to each other, I'm assuming as VL is bigger than VC. And if VL is bigger than VC, first we will add these 2. And if I minus VC from VL, I get this phasor as VL minus VC. What I'm doing, I'm subtracting VC from VL. So we get only VL minus VC. So this is the resultant of these 2. And if I add this resultant to VR, we get supply voltage phasor, which is equal to V naught. So this is the main voltage of the circuit and this is the main current of the circuit, and obviously this represents the phase angle between the main current and main voltage, and this will be called as phi. Okay. If we want to calculate this phi, let us write tan phi, and tan phi would be VL minus VC divided by VR. I think you remember, let me write it here. The VR, maximum voltage across resistor, was equal to I naught times R. The VL was equal to I naught times XL and VC equals I naught XC. Replace VL, VC and VR by these values and you will have tan phi equals XL minus XC divided by R. This numerator is also called net reactance of circuit, and net reactance of circuit will be X by R, right? So tan phi equals X by R. Okay. If you want to calculate here the cos phi, which is power factor. So power factor, if you know tan phi, there is it becomes very simple to calculate cos phi, and you will find cos phi will be equal to R divided by a square root of R square plus X square. So actually this denominator is actually the net effective resistance offered to AC current by the entire three of them, all three of them. So this is called R by Z. Z is the name, Z is given a name impedance. So always remember, in series AC circuit, the cos phi, the power factor is equal to R by Z. And what is Z equal to? So Z equals square root of R square plus X square. What is X square? XL minus XC square, and then we close the bracket. So it is actually the square root of sum of squares of resistance and net reactance of the circuit. The net reactance of the circuit is XL minus XC if XL is bigger than XC. If in some case XC is bigger than XL, it will be XC minus XL. If in some case we do not have a capacitance, X would be only equal to XL. If we do not have inductance, X would be equal to only XC. So that is very simple actually. This is Z. And now I think you know how to find current, because our purpose was to find current. Okay, phi is known now. Phi is obviously known to us. So if you want to find current, the current can be written as, let's write, the current can be written as I naught. The maximum value of current can be written as the maximum value of voltage divided by the net resistance like thing offered by all three to AC current, and which is equal to Z. So this way we can find I naught. So solving AC circuits is not that difficult. First you assume the current like this, you assume its phase difference, you assume its maximum value, and then directly if you have a series circuit, there is no need to repeat the entire procedure. Just remember the value of Z as this is square root of sum of squares of resistance and reactance of the circuit. Okay, when you find Z, the maximum current would be V naught by Z and the power factor would be R by Z. And if you are interested in finding phi, you can also use tan phi equals net reactance by R. And that is the simple summary of LCR series circuits. If we have only inductor and, let me write here, if only L and R are present, if only L and R are present, the Z will be equal to square root of R square plus XL square, because the reactance has only one term XL. Z is this. Tan phi is XL by R. Cos phi is what? Cos phi is R by Z, and I naught is V naught by Z. Simple. If we have only capacitance and R, the Z would be equal to square root of R square plus Xc square, because in terms of reactance we only have capacitive reactance. Tan phi would be equal to Xc by R. Cos phi, as always, R by Z, and I naught as V naught by Z. If you see some circuit where the capacitive reactance is very large, if Xc is larger than XL, because in first case we assumed XL to be larger than Xc, doesn't matter, the Z here would be square root of R square plus Xc minus XL square, and tan phi would be Xc minus XL by R, cos phi R by Z, and I naught V naught by Z. There is one thing you have to remember. From here we guess the value of phi. From here we guess the value of phi. But if we have dominant inductive nature in circuit, that is XL more than Xc, the current will lag. The current will lag, because in pure inductor 2 it used to lag by 90 degree. Here it would lag by some other angle, but in dominant inductive circuit where we have XL more than Xc, the current will lag. If we have a dominant capacitive circuit, means Xc more than XL, the current will lead the voltage. Okay, so here you can guess the value, the magnitude phi, and the angle, the lead or lag term can be decided by this knowledge, that in pure inductive circuit current lags, and pure capacitive circuit current leads. Okay. Now we will revisit power a little bit. As power equals Vrms Irms cos phi, so we can write it as Vrms Irms. As you know, the maximum value of I is maximum value of voltage divided by Z. On similar way, you can write Irms as Vrms by Z, and cos phi as R by Z. So the power can also be written as Vrms square times R by Z. As Vrms by Z is Irms, I can replace Vrms by Irms times Z here. We can also write power as, at the place of Vrms, I can write Irms times Z. We have another Irms, so Irms is square, and times cos phi, which is R by Z. And if I cancel this Z, the P becomes I Rms square times R. If you check this result, you will notice that this is the effective power in resistance, effective power dissipated in resistance, and that is the only power dissipated in the entire circuit, because only resistance dissipates some power. Now it's time to solve few questions based on this study. Here they say we have a series RC circuit and it is connected to an AC voltage source. Okay. And they are saying about two cases. One, when a capacitor is air filled, means there is no insulation between the plates of capacitor, and then when capacitor is mica filled. Now we have inserted insulator or dielectric inside capacitor. So A, we have air capacitor, and B, we have dielectric capacitor. I think you remember, when you put a dielectric in capacitor, its capacity improves by a factor that is called dielectric constant. So capacity increases in B. Okay. If you have only R and C, the impedance becomes square root of R square plus XC square. And do you remember XC is 1 by omega C? 1 by omega C square. So in case A, we have C smaller. In case B, we have C bigger. So if C increases, the Z decreases. Because of this, we have capacitance in the denominator. So we can say as C increases, Z decreases. So ZB is smaller than ZA. And as current is V naught by Z, the current is V naught by Z, so current will be bigger when Z is smaller. So current in case B is bigger than current in case A. So we have only one option, and where the result are opposite, so this option is perfectly wrong. Okay, current in actually A is more than current in B. Current in actually B is more than current in A, because in B case we have a smaller impedance. Okay, so this is wrong, and obviously this is also wrong because the voltage across capacitor, it depends upon current, and current is different. But if you check the voltage across capacitor, you will have maximum current I naught times XC. As current is increasing, if you are filling the dielectric in capacitor, current is increasing and X is decreasing. So it is difficult from here to check whether VC or voltage across capacitor is increasing or decreasing. So we will check some other method. Suppose we are interested in voltage across resistance. So maximum voltage or effective voltage across resistance, say effective voltage across resistance would be effective current times R. Current is increasing, so voltage across R will definitely increase. And as they are in series, if voltage across one is increasing, the voltage across the other will definitely decrease, because the sum, the vector sum, is constant, and which is equal to the effective voltage applied across them. Okay, so as VR is increasing, the VC, that the capacitor voltage, must decrease. Okay, so we must have the voltage in case B is smaller than voltage across voltage in case A. So that is the answer to this question. Next we have this question, and where a circuit connected to AC source and EMF is given to you as function of time, and it gives a phase difference between current and voltage, and the phase difference is pi by 4, and we have to check which circuit is here. So as I think you remember, tan phi is equal to reactance divided by resistance. As phi is pi by 4, tan phi is 1, so the correct option must have reactance equal to resistance. So we have to check the reactance. Check the reactance for all 4. As the resistance is same in all 4, check the reactance for all 4, and you will know the correct choice. So for first option, if we calculate, first one is an inductor, and omega L, let's as I think you remember, the reactance for inductive circuit is XL equals to omega L. So you multiply omega with L. If you multiply omega with L, omega is 100, because the coefficient of T here is omega. So omega is 100. So omega L would be 1000 milliohm. Okay, and 1000 milliohm is obviously not 1 kilo ohm. Okay, it is equal to 1 ohm. So that is wrong. If you multiply omega with this L, this will give you 100 milliohm, and that is even smaller, so it is also cancelled. Okay, let's check this part. So this is a capacitor, and Xc equals, in capacitor it equals 1 upon omega C. Omega is 100 and C is 1 microfarad. So 1 divided by 100 times 10 to the power minus 6 gives you 10 to the power 4. That is 10 kilo ohm. It is actually equal to 10 kilo ohm and it is not equal to 1 kilo ohm. So this is also incorrect. You can check for option D, but definitely this is the only choice left. So D must be the right choice. Okay, next. Here we have a resistance and it is drawing power when connected to AC source. If inductance is now placed in series with the resistance such that the impedance of circuit becomes Z. Okay, so initially we had only resistance, and if we have only resistance, the power P should be equal to effective voltage square by resistance. Obviously, it should be equal to effective voltage square by resistance, because actually it is also multiplied with P. It is also multiplied with a power factor, but power factor is 1 for purely resistive circuit. Okay, so effective power is V square by R. But when an inductor is applied, we have new power as effective voltage square divided by Z and multiplied by cos phi, and cos phi equals R by Z. So this is the next new power. But as V square by R is P, we can put V square as P times R here. So it becomes P times R square by Z square. And obviously the third option or C option is correct choice. Okay, over to next question. Here we have an inductor which is of 20 millihenry, a capacitor 50 microfarad, resistance 40 ohm connected in series across a source of EMF which is 10 sin 340t. What is the power loss in the AC circuit? See, in AC circuit, the power loss is actually I effective I RMS square divided by R. Sorry, I RMS square I effective value of current square times the resistance. So we know the resistance. If we know somehow the value of current, obviously the calculation of power is simple. Okay. So let us calculate. We have to calculate the effective value, that is RMS value of current. Don't forget that. Okay. So first we will calculate the impedance and impedance. Let us first calculate the inductive reactance. That is equal to omega times L. So we have omega L as 340 times 20 times 10 to the power minus 3 ohm. This is XL. Okay. XC. XC is 1 upon omega C. So we have 1 upon omega as 340 times C, and C is 50 microfarad. So 50 10 to the power minus 6, which becomes 10 to the power 6 in the numerator. It is equals to ohms. So we have XL and XC. Okay. Now the Z. The Z would be actually square root of. Actually, this problem is going to trouble you in terms of calculation. Okay. So solve this. So Z would be equal to R square, which is 40 square, plus the net X, that is XL minus XC square. As there is a square of, as there is a perfect square, so there is no need to worry whether XL is more or XC is more, it doesn't matter. We have Z. Now what you do, if you calculate, if you want to calculate RMS, just find VRMS by Z. So VRMS is actually 10. 10 here is a peak value. So RMS value would be 10 by root 2. This is VRMS. And divide this by Z, you will have IRMS. Okay, IRMS. And for calculation of power, just multiply IRMS square with 40 ohms and you will get the right answer. Okay, after all the calculations, you will find the power to be nearly equal to option A, that is 0.47 watt. So that is your solution. Over to next question. In this question, we are given the potential difference across resistance, capacitance and inductance are 80 volt, 40 volt and 100 volt. As the individual voltages are given, let us draw the phasor diagram and check the values. We have to know the power factor of this circuit. Okay. So let us first draw the common phasor, that is current, because in series circuit current is always a common phasor. And I think you remember the voltage across resistance is in phase with current. So voltage across resistance is 80 volt. So this is VR and it is 80 volt. Then we have voltage across capacitance as 40 volt. So capacitance, in capacitance I think you remember current leads voltage, so voltage must lag current. So we have VC as 40, right? VC as 40, and then we have inductance voltage as 100 volt. Inductance voltage as 100 volt. So we have VL, and VL is 100 volt. First we will take resultant of VL and VC. So if you subtract this VC from VL, you will left with VL minus VC, and VL minus VC is obviously 100 minus 40, which is 60. And resultant of VL minus VC and R should be the net voltage phasor V naught. So if we take this angle phi, the tan phi would be equal to perpendicular by base, and perpendicular is 60 and base is 80. So we have 60 by 80, that is 3 by 4. If tan phi is 3 by 4, obviously the value phi is equal to 37 degree. And if phi is 37 degree, the power factor is equal to cos phi, and cos 37 would be equal to 0.8. So the correct option is A, 0.8. Next, here we have a series LCR circuit and it is connected to AC voltage source, and they are saying when we remove the inductor, the phase difference becomes pi by 3. So if you remove the inductor, only the resistance and capacitor remains in the circuit, and the phase difference is pi by 3. So we can write tan pi by 3 as Xc by R, because we have only capacitive reactance at the place of reactance. Now in the next line they say if C is removed, if capacitor is removed instead of inductor, the phase difference is again pi by 3. This time we have inductor and resistance, so I think you will write tan pi by 3. This time will be equal to XL by R. If you compare these two equations, you will notice that these two, they will give you a result that XC equals to XL. Okay, you just divide them and you will find XC equals to XL. So if XC equals to XL, the net reactance, which is equal to difference of these two, is 0. And if net reactance is 0, the impedance is equal to R only. Okay, impedance is equal to R only. And I think you remember the cos phi equals to R by Z. R by Z. If Z is equal to R, the cos phi is nothing but 1. So the correct answer is D. The power factor is actually 1. Next question. Here we have an inductor of inductance L, capacitance of capacitance C, resistance R, and connected across a source of potential difference V. The amplitude of the current is given as 10 root 2, and we have to find the impedance of the circuit. So let me first draw the phasor. Let us say this is the common phasor I naught. We have the voltage across resistance in phase with I naught. So we have VR equal to 40 volt in phase with I naught. We have VC 10 volt lagging with current, and we have VL 40 leading with current. The resultant of these two is going to be VL minus VC, which is 30, and the resultant of VL minus VC and VR will give you the net phasor V naught. Okay, as this is 30 and this is 40. Okay, this is 30 and this is 40, Actually, these are not peak values. Remember, these are not peak values. They are just effective values, means they are RMS values. So this resultant will give you RMS value for V naught. So we can write V naught RMS is equal to 30 square plus 40 square root 2, that is 50. And as you know, the V naught by Z gives you current. So Z equals to V naught by current. Okay. So Z equals V naught RMS divided by I RMS. V naught RMS is 50, obviously 50, but I RMS, we are given that amplitude of current is 10 root 2. So if peak value is 10 root 2, the RMS current would be simply 1 by root 2 of this value, that is only 10. So we have our I RMS as 10, and answer is simply 5 ohms. So D is your perfect choice. Next question. In here we have an arc lamp, and that requires a direct current of 10 ampere at 80 volt. So this arc lamp is actually a lamp or a bulb, you can think, and it operates when the current through it is 10 ohm and 80 volt. So these two parameters will give you the resistance of arc lamp, and it would be 80 divided by 10, that is 8 ohm. If it is connected to a 220 volt RMS supply of 50 Hertz, the series inductor needed for it to work is close to. So what we have to do, we have to connect this bulb or resistance with an inductor, and we don't have to apply 80 volt, we have to apply a 220 volt supply across this. 220 volt 50 Hertz supply across this. Okay, and if we want this to function, the effective current in it must be 10 ampere, because this lamp works when the current is 10 ampere. And the voltage across this lamp at 10 ampere will automatically be 80 volt, because it is a resistance. Okay, so for current here to be 10 ampere, the impedance of this circuit should be, as current is equal to V by Z, the RMS, the effective current, it must be equal to effective voltage, that is 220 divided by Z. So from here the Z is 22 ohm. We know the value of Z. And as the Z is equal to R square plus X square root is equal to 22, we now know the X is equal to 22 square minus 8 square. Okay, this is equal to X, the reactance of inductor, and the reactance of inductor is equal to omega times L. Omega times L. So now you write L equals 22 square minus 8 square is actually 30 multiplied by 14 and divided by omega, and omega here is, as the frequency is 50 Hertz, omega will be 2 pi f, that is 2 pi times 50. So you calculate it well and you will find the option C as correct choice, because the answer will be very close to 0.065 Henry. Okay. Next question. Here we have an LC circuit, means we do not have resistance here, and inductance and capacitance are given to you. The voltage is 10 sine 314t, means omega is 314, and this voltage is applied to the circuit containing inductor and a capacitor, and we are asked what is the current in the circuit. As the current in the circuit, the effective or the maximum current in the circuit, maximum current in the circuit is given by maximum voltage divided by Z, but as we do not have any resistance, actually I think you remember Z is equal to square root of R square plus X square, but R is 0, so it will be square root of X square only. So X is equal to here XC minus XL mod. Okay, So let us calculate XC and XL first. XC equals 1 by omega C, 1 by omega is 314 times C is 100 microfarad. So we have 100 and 10 to the power 6 here. So this is XC in ohms. We have XL as omega L is 314 times inductance is 40 millihenry. So we have 40 times 10 to the power minus 3 ohms. And if you subtract these two, you will find the value of Z. So Z is simply XC minus XL. If you find Z, the current will be given by the V naught by Z. So you calculate it, and if you divide 10 by this Z, the value will be approximately be equal to 0.52 ampere. The maximum value is 0.52 ampere. Now, as you check these terms, you will notice that XC is bigger than XL. Here, you will find XC bigger than XL, and if XC is bigger than XL, the capacitance is dominating in this circuit. Capacitance is bigger, the reactance of capacitance is bigger, so this circuit will behave as an inductive circuit. Okay, and as we do not have any resistance, so we have power factor equals to 0. Means phase difference between current and voltage would be 90 degrees. So obviously the current can be written as I naught, which is 0.52, and as we have sine omega t here, the sine 314 t, but current would be 90 degree leading with respect to voltage as XC is bigger, and circuit is purely capacitive. Because inductance is small, so we have dominating circuit as capacitive. So we have plus pi by 2, and obviously sine omega t plus pi by 2 will be cos omega t. So A is your perfect choice. Okay, so that was your question. Let's move to next one. In AC circuits also, we sometimes need to measure alternating current and alternating voltage. Suppose we apply DC voltmeters and DC ammeters to measure for the measurement purpose, they cannot work here. Why? Because when in DC voltmeter or ammeter, alternating quantities pass through, the average of alternating quantities is 0 and they only read average value. And suppose if you think the pointer of the galvanometer or voltmeter or ammeter should vibrate from plus to minus value, that is not possible because the frequency of the signal is too high, and because of the inertia of the moving parts, they do not respond to high frequency variable alternating currents. Okay, so those meters that like DC galvanometer, DC ammeters, they are not useful here because the average is simply 0. Okay, so if we want to measure alternating current or voltage, some special devices called hot wire ammeter, hot wire voltmeter are used there, and they measure the effective value. Remember, if you see AC meters, it must be written there, AC meters or hot wire instrument. Okay, so whenever you see terms like this, always remember they always measure effective value of current or voltage, and that effective value is simply RMS voltage. Okay, so now we will study a special feature of LCR circuit, that is series LCR resonance. What is a series LCR resonance? Okay, or what is the meaning of resonance? Resonance in AC circuit. Whenever resonance occurs in AC circuit, the only and the most important condition is the power factor. The only condition here is the power factor of the circuit, the power factor, that is cos phi, must be equal to 1. Okay, if cos phi, a power factor of the circuit, is 1, we say the circuit is a resonance. And now let us see what will happen if circuit is in resonance. As we know, the power factor is equal to R by Z. Okay, this means if power factor is 1, the Z will be equal to R. And remember, the Z is always more than R because of the reactance term. So if Z is equal to R, this is the minimum value of Z. So remember, Z is minimum at resonance. Z is minimum at resonance. As you know, the effective current is effective voltage by Z. So as Z is minimum, the I is maximum at resonance. So the maximum value of I can be given as I maximum is equal to, this is actually the effective value of maximum current or RMS value of the maximum current, and it is equal to effective value, that is RMS value of the voltage divided by Z. But Z is equal to R here. So I max is simply VRMS divided by R. Remember this point. Also, as Z is equals to R, means the reactance part of the circuit must be 0. And if reactance is 0, as you know, reactance is the difference of XL and XC. So if reactance is 0, the XL must be equal to XC. If you put their values, XL is omega L and XC is omega C. So these two get equal at a spatial frequency called resonance frequency. So if the circuit is in resonance, the frequency is equal to, or the angular frequency is equal to 1 over root LC, or the frequency, the resonant frequency is equal to 1 upon 2 pi root LC. These are very important concept. You all must have to remember them, and all can be derived using a single condition, that the power factor is 1. Okay. Also, suppose we have an AC circuit or a series RLC circuit where we have a AC voltage, an inductor, a capacitor and a resistance, and we somehow vary the angular frequency from a very low value to a very high value. If we plot the reactance, okay, so as you know, the inductive reactance, that is XL, is omega times L. It must be proportional to omega, and as omega increases, XL increases because XL equals to omega L. So the plot is a straight line passing through origin. But XC means capacitive reactance. As it is equal to 1 by omega C, it varies rectangular parabolically with omega, and the graph should be something like this. This is XC, which is equal to 1 upon omega C. And can you see at this frequency, call it omega R, they both are equal. XL equals XC. And this is the condition where we get resonance. Here the impedance is minimum and the current is maximum. Also notice, when omega is equal to omega R, we have XL equals to XC. As the net reactance is difference of the two, the net reactance is 0. Okay, and if net reactance is 0, circuit is purely resistive. Purely resistive. Yes. Now what if we decrease the omega? If omega is less than omega R, can you see from the diagram? If omega is less than omega R, the omega C, sorry, XC is bigger than XL, because XL is at this frequency, XL is this, XC is this. XC is definitely bigger than XL. XC is more than XL, and if XC is more than XL, means capacitance is dominating here. The capacitance is dominating here, and the nature of circuit is capacitive. And if nature of the circuit is capacitive, current will lead the voltage. We can write I, the current leads. But what if omega is more than omega r, means resonant frequency, we have XL more than XC. If we have XL more than XC, if XL is more than XC, the inductive reactance is more than capacitive reactance, and therefore the nature of the circuit or the AC circuit is inductive, and here current lags. So these are few points, you should keep them in mind. If we plot the current versus omega, and we again vary omega from a very low value to very high value, you know at resonant frequency current is maximum, and if you decrease omega or you increase omega, in both ways the impedance will be higher than the resonant condition impedance and the current will be lower. So the current plot is something like this, and current is maximum at resonant frequency. Always remember, this current is called maximum value of effective current, like this. If current is maximum, the power in the circuit is maximum. If current is maximum, the power in the circuit is maximum, and if we decrease the current by I max by root 2, okay, if current is decreased by 1 upon root 2 times, the power will be reduced by half, because power is proportional to I square. So if power is reduced to 1 by 2, so we can say here if current is this, we will be getting half power, and half current, half power we get at two frequencies. One is say omega 1 and other is omega 2. These omega 1 and omega 2 are called, they are called half power frequencies. Omega 1 and omega 2 are called half power frequencies. They are called half power frequencies. Also remember, omega 1, omega r and omega 2 are in geometric progression. As you can see, the omega r lies between omega 1 and omega 2. After some calculations, not very difficult calculations, you can guess omega 1 and omega 2, and actually omega 1, omega r and omega 2 are in geometric progressions, and omega resonant is actually the geometric mean of omega 1 and omega 2. As the circuit is in resonance, remember, as the circuit is in resonance, the voltage across capacitor and inductor has same effective value, is always same. Why same? Because XL equals to XC, and if XL equals to XC, VL2 must be equal to VC. But remember, by phasor, VL and VC are in opposite direction, so effective voltage across L and C is 0. Net potential difference across L and C is 0. As XL equals XC, therefore VL also equals VC. Okay. In this case, the potential difference across inductor divided by potential difference across resistor is called quality factor of the circuit, represented by Q. Quality factor or Q, and Q is given by actually potential difference across inductor or capacitor divided by potential difference across R, means VL or VC divided by R. So this can be written as XL by R or XC by R. If we place the value of XL, actually XL is omega L. As resonance is occurring, you will have Q as omega R L divided by R, and if you put the value of omega R here as 1 over root LC, you will get 1 by R root L by C. So these are few facts about resonating circuit, and please remember them all, and let us solve few problems based on these. So here in this question, we are given an LCR circuit, series circuit, and across L, C and R, we have applied AC voltmeters to read their values. They are saying what is the value of the voltmeter across resistors. Can you see the voltage across inductor and voltage across capacitor are same? Both are 300 volt. And if both are 300 volt, obviously it can only happen when XL is equal to XC. If XL is equal to XC, means the circuit is in actually resonance. And if circuit is in resonance, the current is maximum, and the current will be equal to effective voltage divided by Z, and the value of Z is R only. As V is 220 and R is 100, we get current as 2.2 ampere. So the effective value of current is 2.2 ampere only. And obviously the VR, as VR is given by I times R, this will be equal to 220 volt. So we have D, the correct choice, as voltage across resistor is 220 volt and the reading of ammeter, the AC ammeter, will be effective current, that is 2.2 ampere. Okay, so that was this question. Let's move to next one. Here we have again a series LR circuit. Okay, and the power, it is consuming power of 400 watt, and 400 watt is being dissipated from a source of 250 volt 50 hertz. The power factor of the circuit is 0.8 amp. So if you remember the formula for power, I think power you remember as is the effective value of voltage, the effective value of current, and power factor cos phi. So I here equals power divided by V cos phi. Power is 400, V is 250, and cos phi is 0.8. Let us solve these, and if you solve this, you will find current as 2 ampere. So the effective value of current is only 2 ampere. Now they are asking that to make the power factor of the circuit unity, means we have to bring the circuit into resonance. If we have to make the power factor of the circuit unity, what capacitance will we have to add in it? Okay, so actually, if you know the value of inductive reactance, the same should be capacitive reactance, as in resonance XL and XC are same. So let me calculate a little more. As you know, I think I is equal to effective value of voltage divided by impedance. You can calculate impedance equals to V, which is 250 divided by I, which is 2 ampere. So Z will come out to be 125 ohms. This is the value of Z. Okay. And also, as the power factor of the circuit is 0.8, you can write cos phi as 0.8, that is 4 by 5. From here you can say the phi equals 37 degree, right? And if phi equals 37 degree, tan phi, I think you remember, is x by r. So this is equal to tan 37, which is 3 by 4. This will help us a lot. Now we can write, remember, notice, Z equals to R square plus X square. I'm talking about the LR circuit only, because the impedance of that LR circuit is 125 ohm. So Z square actually R square plus X square. So from here I can place R as 4 by 3x, and if I place R as 4 by 3x, we'll be having 125 square equals 16 by 9 x square plus x square. That will be equal to 25 by 9 x square. If you solve from here, you will notice that x is going to be, what is x going to be? So let's cancel, x will be equal to 75 ohms. X will be equal to 75 ohms. And if this is x, or you can say if it is XL, the same equal amount of XC should be added so that the net reactance of circuit may become 0 and the circuit may come into resonance. So let me write few more words. As XC equals to XL, so XL is 75, we have XC also as 75. We can write XC as 1 over omega C, but do we know omega? Yes, we know omega. As the frequency is 50 Hertz, the omega will be 2 pi times 50 multiplied by C. So from here, I think you can guess the C is going to be 1 divided by 7500 pi farad. Okay, and if you compare this result with this one, n upon 3 pi microfarad, if you compare this by n upon 3 pi microfarad, you will find n equals to 400. So this is your answer. Here n is equal to 400. Over to next question now. Here we are given again an RLC circuit with voltage of amplitude Vm and frequency omega naught equals to 1 over root LC. I think you remember, if we have this frequency, the circuit should be in resonance, because at this frequency XL and XC are same. So we have been asked what is quality factor of the circuit. I think you remember the quality factor of the circuit is given by XL by R, and XL can be written as omega L, but omega is angular frequency omega naught by R. So omega naught L by R is the right quality factor, and therefore option C is obviously correct. Okay. Next question. Here we have an AC circuit that has R as 100 ohm, the capacitance as 2 microfarad, inductance 80 millihenry, and they are connected in series. The quality factor of the circuit, what is the quality factor of the circuit? In terms of LC and R, I think you remember the quality factor is given by 1 over R root L by C. You put all the values of R, L and C and you will find very easily that quality factor of the circuit is 2. So B is your correct choice. Here again we are given a question, and in this question we have a capacitor and R2 in series, an inductor and R1 in series. These both branches are in parallel and they are connected across a AC voltage source. Now actually the current in LR is I1 and the current is RC or CR is I2, and we have been asked what is the phase difference between I1 and I2. Actually this question was declared as a bonus because here the value of C was given as root 3 by 2 microfarad. Okay, but I have made it correct by assuming it to be millifarad, and now the option will be chosen. So here let us analyze this circuit with the help of a phasor circuit. So let us observe this circuit first, which is an LR series circuit. In LR series circuit, we have current I1 as common phasor. So if we draw I1 as common phasor, we have VR1 means voltage across R1 in phase with current, because in resistance voltage and current are in same phase. So we have VR1 in same phase as current, and in inductor the voltage leads current. Remember, the current lacks voltage and the voltage leads current. So the VC must be like this. Obviously, the resultant of VR1 and VC must give us the net voltage across them, and net voltage across them is actually the supply voltage, let's say V0. Okay. So clearly the I1 lacks V0 by some angle, let's say phi 1, and this tan phi 1 can be written as VC upon VR1, and VC upon VR1, VC upon VR1 can be written as XC divided by R1. Okay. XC can be written as 1 over omega C R1, and let us put the value. If we put omega as 100, C as root 3 by 2 millifarad, and R1 as 10, you get this value equal to 1 over root 3 actually, and this says the phi 1 is 30 degree. So I1 lags with V0 by an angle 30 degree. Similarly, if you draw I2 in a different diagram, VR2 is in phase with I2 and VL lags I2 by 90 degree. The resultant of VL and VR2 should also give V0, because V0 is the voltage that is across this branch, and that too is across this branch. So we have this angle as say phi 2, and let's calculate phi 2. So tan phi 2 will be equal to VL upon VR2. This becomes XL divided by R2, and as XL is omega L divided by R2, you put all the values of omega L and R2, and this value is equal to root 3. That gives you phi 2 as 60 degree. Now if we merge these two, can you see in these two diagrams, the V0 is a common voltage, a common phasor. This V0 and this V0 is same. So let us first draw V0. Then the I1 can be drawn 30 degree lagging with respect to V0. So I1 lags V0 by 30 degree, as phi 1 is 30 degree, you can see from here. And I2 leads V0 by 60 degree, as phi 2 is 60 degree. So I2 leads V0 by 60 degrees. And obviously the phase angle between I1 and I2 is 60 plus 30, that is 90 degree. So 90 degree is the correct choice. So this is the correct choice if we suppose the capacitance in millifarad, okay, in millifarad, or R1 in kilo ohms. That is the only choice. If we assume all the data that were given exactly as in questions, we will get the phi 1 nearly as 90 degree, because in that case the tan phi 1 will be a very big value, 10 to the power 3 by root 3, and in that case phi 1 would be approximately 90, and then the answer would be approximately 150. So that is obviously not matching with any of the options. Next question. Here again they are saying, I think we have done this question before. Okay. A sinusoidal voltage of peak value 283 volt and angular frequency 320 hertz, and this is applied to an LCR circuit. If R is 5 ohm, L is 25 millihenry, C is 100 microfarad, the net impedance, we have to find the net impedance and the phase difference between voltage and current. Okay, so let us find this. As R is given, let us first calculate XL. and XL is actually the omega times L. Okay. As angular frequency is 320, angular frequency, remember omega is given. So as angular frequency is 320, XL will be 320 times inductance, which is 25. And if you multiply these two, this will be equal to 8 ohms. So this is 8 ohm. If you find XC, XC is 1 over omega C. Omega is 320 times C, and C is, where is C? Where was the C is 100 microfarad. So C has 100, 10 to the power 6. And if you calculate this, you will find XC nearly, very, very close to 3 ohms. So we have XL as 8 ohm, XC as 3 ohm. So if we find the impedance Z, which equals square root of R square, which is 5 square, plus XL minus XC. XL minus XC is 8 minus 3, that is 5. So we have 5 square. This is not a very exact, but approximately it is 3. So this is almost 5 square. And this comes out to be 5 root 2. And 5 root 2 is nearly, or you can say it is very close to 7 ohms. So we have impedance as 7 ohms. Okay. And if we have impedance as 7 ohms, let me find the angle. Okay. As you know, the tan of angle between, or phase angle between current and voltage is given by net X by R. And see, the net X is 8 minus 3. So it is nearly equal to 5 upon 5. So it is equal to 1. Nearly equal to 1. And if it is nearly 1, 5 would be very close to 45 degrees. So we have correct option as B. The impedance is 7 ohms and the phase angle is 45 degrees. Now we will study an old topic. I forgot to mention this in previous chapter. So this is eddy currents. This is not difficult to understand, but suppose you have a magnetic field. You have a magnetic field at some place, and we have a metal block or metal piece, and there is relative motion between magnetic field and metal. The shape of metal block can be of any sort. It can be of a sphere, it can be of any type like cube or pyramid or rod. It may be of any shape. But if this metal piece moves with respect to magnetic field, the flux inside metal changes. And if flux inside metal changes, induced currents are produced. But as there is no fixed loop, it is just a solid metal block, the shape of induced current is undefined. In entire volume of the metal, the random loops form, but the purpose of this induced current is to oppose the change, okay, oppose the cause, and the cause of this induction was actually relative motion. So the induced current produces such a force that the force opposes relative motion. So if relative motion between metal piece and magnetic field is like this is relative motion. The force is like this. The magnetic force is like this, according to Lenz's law, remember. So whenever a metal block or metal piece moves in magnetic field, opposite or a force acts opposite to the relative motion, and that is because of induction of large random shaped current loops inside metal piece. These currents are called eddy currents, okay, and they always opposes relative motion. Always opposes relative motion between iron piece or metal piece, metal, and magnetic field. A very good example of eddy current was this moving coil galvanometer. I think you remember I talked about this, that whenever the magnetic torque and spring torque becomes equal, there is equilibrium of the coil or there is equilibrium of pointer. But at the position of equilibrium, the pointer vibrates a little and then it halts, then it stays. So to avoid these vibrations, we need some damping. We could have used air friction damping or oil friction damping, but we do not use any additional damping here because this soft iron core acts as a very good electromagnetic damping. How? When the coil moves, the soft iron core also moves along the coil because the coil is tightly wounded on this soft iron core. And when this soft iron core moves inside this magnetic field, there is relative motion between the soft iron core and magnetic field. And that produces eddy currents or the induced currents in this soft iron core, and they always oppose relative motion. So if the coil is vibrating or trying to vibrate, the eddy currents, the force by eddy currents or the torque by resistive torque by eddy currents stop their relative motion, and this quickly makes the oscillations to die out very quickly, and we can take the reading precisely. Okay, so that was the meaning of eddy currents. Okay, and now let us understand the last topic of this chapter, which is transformer. Let us understand what are transformers. In transformers, we have two coils which are magnetically coupled with each other. So we have one coil this and one coil this. They are magnetically coupled. Let us say number of turns in first coil is N1 and the second coil is N2. We also call it primary coil and secondary coil. In ideal transformers, we do not have any resistance. So in ideal transformer, net resistance is 0 and power loss is also 0. Now when we apply some AC voltage here, let's say V1, alternating current I1 develops here. Actually, I1 is alternating, but it still have given a positive sign. It doesn't mean it is always in this direction. It is always flipping. Sometimes it is in right direction, sometimes it is in left direction. So this alternating current actually creates a alternating flux. It creates a flux. Some of this flux may also pass through the secondary coil. But here we make some spatial arrangements. Some spatial arrangements are made, and the flux created by the primary coil, let us say phi, somehow links both the coils equally. So we can say in ideal transformer we have full linking of flux. How it is achieved? We use a metal frame that links both the coil. So we use a metal frame here like this. And when magnetic field lines find a metal path, they don't go just anywhere else. They follow this metallic path and they cross the primary coil and the secondary coil equally. So somehow using a metal core, we achieve the same flux produced by I1 link the secondary coil. Okay. This way, if this is the flux, as I1 is varying, I1 is alternating, the flux phi is also alternating. And if flux phi is also alternating, the flux linked with coil 1 and coil 2 changes with time. And if flux linked with coil 1 and coil 2 changes with time, it creates an EMF, an induced EMF in primary and secondary coil also. The primary coil, in primary coil we have induced EMF as V1, and that is equal to minus N1. What is N1? N1 is number of turns in primary coil, N1 d phi by dt. This is according to Faraday's law. And we also have an EMF induced in the secondary coil V2, and V2 is equal to minus N2 d phi by dt. If you divide these two, you get V1 by V2 as N1 by N2. So can you see the V1, the voltage is proportional to number of turns. So if here we have large number of turns, here we have bigger voltage. If here we have a smaller number of turns, we have a smaller voltage. Okay. Also, as there is no power loss, power input should be equal to power output. As power input is I1 V1, power output is I2 V2, we have I1 by I2 as V2 by V1, and V2 by V1 is equal to N2 by N1. So we have current inversely proportional to the number of turns. These are the two fundamental formula for transformers. Let us understand how this transformer works. Let me give you a very practical example. Suppose we have a generating station where electricity is produced. The electricity is produced at a certain voltage, and let us say that voltage is 30 kilovolt. Actually, most generating stations are at 33 kilovolt, but for the sake of simplicity of calculations, I am using 30 kilovolt. Okay. Suppose this generating station is of 33 megawatts, but again for the simplicity of calculations, I am taking the power is 30 megawatt. So if power is 30 megawatt, as power is V times I, let us divide P by V, we get current. So the current here is 30 megawatt divided by 30 kilovolt, we have 1000 amperes. So the current here generated is 1000 ampere. Okay, that's a big current. Suppose we have to transmit this power at a very distant location, and this location is 500 kilometer far from the generating station, right? Let us say actually we have to carry a large current, and for carrying large current the wires too should be of very high strength, and that can be achieved by taking a big cross section wire, a very thick wire. So wires are very thick, and let us say resistance of wire is only 0.1 ohms per kilometer. That is a very small resistance. Obviously the wires are thick, the resistance is small because R is proportional to 1 by A, 1 by cross sectional area. So if we have 0.1 ohm resistance per kilometer in the lines, in 500 kilometers we have 50 ohm resistance. And if resistance of lines is 50 ohms, there will be losses in lines. And what are the losses? Losses equals I square R. What is I square R? I square is 10 to the power 6. R is 50 ohm. So we have 50 megawatt loss. Isn't this weird? Because we are generating only 30 megawatt, and the losses required are 50 megawatt. Okay, suppose we generate here more than this value, almost all the energy will be destroyed in path and very low energy can reach this point. So obviously this transmission thing, this transmission of energy is not very practical. We cannot transmit this energy to distant locations. So what is the solution? That the solution lies in the discovery of transformers. Okay, so let us understand how it works. Suppose again we have a generating station that produces electricity at 30 kilovolt. This is a 30 megawatt plant. Obviously the current here is 1000 ampere. Let us put here a transformer. And transformer is such that the turn ratio here is, let us say, 1:1000. 1:1000. Okay. So number of turns here and here are in the ratio of 1:1000. So because number of turns are increasing, the voltage will increase 1000 times. So if here at the primary side we have voltage as 30 kilovolt, at the secondary side we'll be having voltage as 30 megavolt. Voltage increases by a large factor. That is why few lines you must have heard about, few lines are called high tension line, HT lines, because the voltage is very high. Okay, if voltage is very high, the current is actually inversely proportional to number of turns. So if voltage increases 1000 times, the current here becomes smaller than 1000 times. So current here is only 1 ampere. Now we have applied a transformer, the cost increases. Let us decrease this cost by using very thin wires here. And if wires will be thin, the area of cross section will be small and the resistance will be more. So let us take the resistance of line as 100 ohm per kilometer. We are taking very thin resistance. Resistance is 100 ohm per kilometer. If resistance is 100 ohm per kilometer, the 500 kilometer resistance should be ohms. And if we now calculate the power loss is I square, so 1 ampere square times R, and this will be only 50 kilowatt. 50 kilowatt or 0.05 megawatt. So if we are generating 30 megawatt, the loss of 0.05 megawatt can easily be tolerated, and that is why transformers are very essential. They are very essential. We cannot take this advantage with DC currents, okay, because if we send DC current in transformer, the flux would be created, but flux will not change with time. And if flux doesn't changes with time, the EMF will not be transferred here because the flux is not changing. So with DC, the transformer cannot act, and the transmission of DC current over a long distance with very high efficiency is not possible. Okay. So I think now you understand the concept of transformer. If the voltage level increasing, and current level decreasing, this type of transformer is called a step up transformer. But at the user side, means at this end, where we need smaller voltages, we can reverse the process and can use a step down transformer. Okay, here we have number of turns decreasing, so we have say number of turns decreasing. Here we have 1000 turns, here we have 1 turns. So again, large amount of current can be obtained because current will increase now and voltage will decrease now with equal factors. Okay, so at the user end also we also have transformers. So if we have to transmit electricity over large range, two transformers are applied. First at generating side, that increases the voltage and decreases current. Then this decreased current is transmitted, and then at the user end where we consume electricity, again we use transformer to decrease voltage again and increase the current again because current is needed. Okay, so that was the advantage of transformer. Let us understand few, or let us solve few more questions about them. We have a transformer consisting of 300 turns in primary and 150 turns in secondary. So we have large number of turns in primary and less in secondary. These are 300 and 150. Now they say that the output power is 2.2 kilowatt, or that is the output power is 2200 watt. Okay, the current in secondary coil is 10 ampere. So here we have 10 ampere, and they are asking us what is the input voltage and input current. Okay, so the if input voltage is say V1 and say current is say I1. Let us say output voltage is V2. Okay, as the output power is 2200, I can say the V2 times 10 equals to 2200. So V2 equals 220 volt. V2 is 220 volt. If V2 is 220 volt, we remember V1 by V2 equals N1 by N2, that is 300 by 150, which is 2. So we have V1 as 440 volt. So we have input voltage as 440 volt, and obviously as voltage here is 440, here we have 220. So in this direction voltage is decreasing, so current must increase. So at this side we must have half of the current, that is 5 ampere. Okay, so the correct option, the correct answer is C, 440 volt and 5 ampere. Okay, you can also apply I1 by I2 as V2 by V1. As I2 is 10 ampere, V2 is 220, V1 is 440. From here also you can get I1 as 5 ampere. That was a very simple question. Let's talk about this one. Here we have a power transmission line, and the input power is 23 volt. The input power is at 23 volt. So input voltage is, we have a transformer here, and input voltage is at 2300 volt. So voltage here is 2300 volt, and this is a step down transformer, means the number of turns are decreasing on secondary side. Primary winding has turns 400, and the primary winding has 400 number of turns. Let us read the question. The output power is delivered at 230 volt. So here we have 230 volt. As you remember, I think V1 by V2 is equal to N1 by N2. By putting V1 and V2 here, N1 and N2 here, you can easily notice, you can easily calculate the number of turns here are 40. Now they are saying if current in the primary of the transformer is 5 ampere and efficiency is 90%, what is output power? So current here is 5 ampere. Okay, let us calculate the input power. So input power should be 2300 times 5. This is input power. As only 90% power is available on secondary side, let's multiply it by 90 by 100. Only this power is available on secondary side. So this should be equal to secondary side power. The secondary side power should be 230 multiplied by I2. Let's calculate. Let's cancel this. Let's cancel this. and let's cancel 230 by 230. We have I2 as 45 ampere, and that is your answer. So correct answer is B, 45 ampere. So thank you students. I enjoyed a lot this session, and I hope you will be benefited by this session a lot. Thank you so much.